Good morning, everyone. Hope you had a nice weekend. Today, the main concept that we'll look at is variation of parameters. It's a way to solve for a particular solution or to find a particular solution more generally than what we've seen so far. But just using the technique itself, I don't think is incredibly deep. It's more looking at some particular formulas and knowing what to substitute in, and then just working with the integration and kind of the algebra. But before anything else, let me give a few announcements. Day 18 and day 19, which would be Wednesday and Thursday respectively, they're currently available, or actually not currently, they will be available at 9:15 today. These will be similar to the last review, I think it was day 9, where they are more questions than usual, several more questions than usual, and the questions may be more in depth or what have you, but they're certainly similar to questions you will see on an exam. So I think they're good practice. Last exam, people's performance was pretty strongly correlated, positively correlated to how they did on the review. So I would tackle those reviews whenever you get a chance. And then at the same time, written homework 4 and lab 4 are doable currently. Lab 4 is in fact just looking at Euler's method, something you've done. It's just doing it in a lab format. And written homework 4 is 2 questions. I just looked at them, but then I forgot exactly what they were. But they're something you could do like right now they're very accessible. Hopefully we'll get a chance to look at them today to help you get started. But at any rate, whenever you get a chance, I'd start looking at day 18 and 19 early so you don't have to feel rushed at the last minute to try to get them done because they are more questions than usual. And right, I think let's just jump into questions then. So specific questions that you guys have you want to ask. So someone asked about written homework 4, question 1. Yeah, I would certainly like to go over those. Let's save those maybe for after the other topics here. But yeah, we'll definitely try to get to written homework 4, question 1. Someone else asked, lab 3 graphing dp dt versus p. Sure. So let's look at lab 3 and then look at dp dt versus p. I'll bring up lab 3 here, and we're looking at so if you're looking at the constant harvesting model, in particular, that will look like, in this case, dp dt is equal to 0.18 times p times 1 minus p over 50,000. And then since we're doing a constant harvesting, we'll take away h. Now, saying that supposing that h is some given value, like a set value, it's not determined, but it's going to be a constant, then we can rearrange this. And even if not, we can still rearrange it, but keeping that in mind, that we'll eventually look at it like a constant. What we end up with is negative 0.18 times p squared over 50,000 plus 0.18 p and then minus h. And again, think of this as h just being some real number. Now, if we look at this in terms of graphing, suppose for a second I do a switch, and in place of dp dt, I write y, and in place of p, I'll write x. Then what you get is a polynomial that maybe you're more familiar with. Now, you don't have to do this switch out. This is just to perhaps make it easier to see what's happening. This is just some second degree polynomial. And that's all there is to it. If you have a second degree polynomial, no matter what, it's just going to be a parabola. That parabola is going to be shifted around, but it'll be some parabola. And you can even tell whether it opens up or down based on what the coefficient is in front of the x squared. Since the coefficient is negative, like here, we'll have a parabola opening downward. And it'll look, let's see, depending on h, might look something like that. What you're asked to do in that problem, or in parts of this problem for this lab, is to find the equilibrium solutions. That is, find where this is equal to 0. And this, if it's modeled by this curve, this, let's say, magenta curve, you're going to find out where that intersects this axis. Now, I could just relabel things up here. And instead of calling this the y-axis, I can revert back to this name dp dt. And then I can call this p. But the curve is going to be exactly the same. It's going to be a parabola opening downwards like this. So again, finding the equilibrium points means finding where this is 0. That is, where the slope is 0. So finding where this curve intersects the p-axis. So hopefully that kind of explains what you're doing with the dp dt versus p. You're really just looking at this as a second degree polynomial MP. Then someone asked about question 2 in the written homework. I'm assuming that's written homework 3. So let's show any separable differential equation is also exact. Let's look at that. This would be written homework 3, number, I guess, 3.2. You want to show that separable implies exact. If you're separable, that'll be first order. You have dy dx is equal to some function of y times some function of g, like so. And now we want to try to show that this is exact. One thing we can do is first separate it. So we might get something like 1 over f of y dy is equal to g of x dx. And now, to fit the format for being exact, we have to set it up so that it's something times dx and then something times dy. And we're adding that together on one side. Doing so will give us this. And now, in order to check it's exact, we check a set of partial derivatives. The partial derivatives we check is we take the expression in front of the dx, whatever it is, and we take the partial with respect to y. So we take partial with respect to y of g of x. Then we take the partial with respect to x of this thing in front of dy. And then we check, are they equal, question mark. If they are equal, it's exact. If they're not, then it's not exact. And of course, if you have a function of x, that means taking the partial of y is taking the partial of something that's completely constant. With respect to y, x is considered a constant. So if all you have are constants, like actual real numbers, and x, y sees that as all constant. Therefore, this partial derivative is going to be 0, And it's exactly the same over here, where you're taking the partial derivative with respect to x of something that only has y in it. So that's also 0. And of course, 0 is equal to 0. And that implies that we have an exact equation. So we started with separable here, and then we just separated the variables, rewrote it, did a check, and then we see that it's exact. Okay, let's see what other questions we've got here. Going back to lab 3, some of you are asking about the proportional harvesting. So with the proportional harvesting as compared to the constant, and let me just say quick, with the lab 3, we had essentially 3 models, dp, dt, where there's no harvesting. We had the constant harvesting. Actually, I can just copy this. And then we had the proportional harvesting, where this is minus h, and this is minus e to the p. So proportional. This is constant. And this is no harvesting. So here were the 3 models. In the no harvesting case, you just don't take anything away. The population grows according to, the natural, its natural parameters. It's just going to grow in its natural way. You're not going to mess with it. With constant harvesting, you're going to take away a set amount. For example, every Wednesday, you're going to remove, let's say, 1,000 fish from your fishery. In the proportional harvesting, you won't remove a constant amount. The amount you'll remove depends on how much there are. So you could say something to the effect of, instead of always a set amount no matter what, the amount you'll remove depends on how big the population is. So if you have a population of, let's say, 1,000, and you remove 10% of that, you're going to remove 100. If you have a population of 100,000 and you remove 10% of that, you remove, 10,000. Or if you have a population of 100,000, you remove 10,000. So it really depends on the population itself. This E, since you're taking a proportion, this E is going to be somewhere between 0 and 1. So if your population is, let's say, 50,000, and you're taking away 10,000, then you'll take away 5,000, and so on. So that's between 0 and 1. But mathematically, it's nothing fancy. It's just a constant number. So what you can do is you can rearrange this equation, and I think what you get is something to the effect of 0.18p minus e to the p, and then minus 0.18 over 50,000 times p squared. And that, of course, would simplify down to this, negative 0.18 50,000 p, and then we would have plus 0.18 minus e, and then that's multiplied by p. So that's with a little bit of simplification. And then you see, if you want to find out where the equilibrium is, it's actually pretty straightforward. I've factored it so that we could just see p is 0, and then p is going to be equal to whatever it needs to be so that this is 0. So you have 2 possibilities in that case. So it's actually a little easier, at least to work with in that sense, than the constant harvesting. Okay, so hopefully that gives a little more detail on what was happening in lab 3. Let me look at the chat here. Oh, and if you want to find the solution, or if you, in the end, want to look at EP, what that's really just saying is, to this, one can find a solution P of T for the population. And then you can correspondingly look at the proportion of P of T that you're taking away. So as P varies over time, you can say, well, each time we look at P, let's look at a proportion of P instead. So if the population is 5,000, you're taking away 10%, then E of P becomes 500. And so on. If the population is now 100,000, all of a sudden E becomes 10,000. So it's just modifying whatever your population is that's changing. It's just taking a proportion of it, just so you can see over time how much or how many fish or population you're removing. That's really it. Okay. Some other questions we're just asking about written homework 4. So yeah, let's look at this material and then try to get into written homework 4 so we can get you an early start on that. So first, a little bit of a review. We have done particular candidates in specific cases. That is, we've determined what the particular candidates are for the cases of polynomials, for exponentials, and then finally for trig. And when I say trig functions, I really mean sine and cosine. So what we would do is we would look at some differential equation, linear constant coefficient. It would be non-homogeneous. And then when we look at this ft, we would have one of these three cases. We would have a polynomial, we would have an exponential, or we would have a sine cosine. Depending on what we had, and depending on how it compared to the complementary solution, we would then choose a particular candidate in a certain way. There was a set way to do it. So depending on what your f of t were and what your L of x were, you would choose a particular candidate in the polynomial case to be something like, let's say, a sub 0 plus a sub 1t plus a sub 2t, and etc., up until we got to some a sub n, t sub n. This should be t squared. Same thing with exponentials, where you would actually have the same polynomial in general, and you simply multiply by some e to the alpha t. And then with trig, namely sine cosine, we would have two different polynomials where each one is multiplied by sine or cosine, and they should be different. When looking at homogeneous differential equations, this is what we've done so far. We've looked at the linear constant coefficient non-homogeneous differential equation. We would find the complementary solution, and then depending on what was in that solution, we would then go ahead and use a particular candidate that looked like this. Every case, there's a general polynomial, and it's really just a matter of whether we leave it as a polynomial because f of t is a polynomial, we multiply an exponential by a polynomial, or we take a combination of cosine and sine, where each one is multiplied by their own polynomial. And the degree of this polynomial depends on what is in f of t and what is in the complementary solution. Let's maybe look at a quick example just to remind us. We would have to do some pseudo count. Essentially counting the repetitions, quote unquote. So suppose that we had, let me think really quick. X double prime plus I guess 9x is equal to the following here, t cubed cosine of 8t. If you find the complementary solution to this, that will end up being c1 cosine, actually, whoops, let me change this to 3t, and so it's not too confusing, let's change this to 4t. If you have the complementary solution at c1 cosine of 3t plus c2 sine of 3t. Now, when you look at the complementary solution, you have a cosine 3t. When you look at this non-homogeneous part, you also have a cosine 3t. The fact that there's a t to the fourth here in some sense means that there's a pseudo repetition of cosine. And now we do a count, and we can think of there being 5 repetitions, and here being 1 repetition. Then together what we need, or will want, in order to make sure we get the right particular candidate to begin with, is we'll take the particular candidate to be cosine and sine, so cosine of 3t and then sine of 3t, and then we multiply by a polynomial. In each case, the polynomials are different in general. The polynomial we multiply depends on this count. We add 5 here. I've called that in the past a pseudo count. 5 here and then 1 here. Add that up, that's 6. So what we want to do is multiply by a polynomial with 6 terms. And if we start with a term that does not have t in it, we start with, let's say, a0, and then we add 5 more terms, that means we're going to go a sub 1, t, a sub 2, t squared, so on and so forth. Now, there's more to it that we'll skip for now, just because finding the second derivative of this would be just kind of cumbersome and not really illuminating. The big thing here is to just know what you're going to pick for your particular candidate. And to relate to what we're looking at today, the fact that we know what we should pick in general. It's very likely that many of these terms will go to 0 when you do all the algebra in the end. But we at least know for sure what we should pick that's going to work for sure. There's some kind of set rule. But it's not always the case that we'll have either sine, cosine, exponential, or polynomial. We may have a different trig function. We may have totally other functions that are not polynomials, are not exponentials. That could be rational functions and so on. So we would like a technique, if possible, to tackle other cases as well besides these 3 cases. And that's where this comes in, finding a particular solution in general. Now let me actually remove some of this just so you don't have to focus on too much at once. This is a technique we'll apply to second-order differential equations that are linear, and in particular, they'll be non-homogeneous here. So say you have such a differential equation, it's linear, second order, non-homogeneous. If we find the complementary solution, and we suppose the complementary solution looks like this, then what we can do is, no matter what f is, get some formula for what the particular solution would look like. In particular, if we have a y2 and y1 components of the complementary solution, and we know what this part is, the quote-unquote non-homogeneous part, then we can use this formula. Now, you can derive this formula, but I don't know that showing you it will be terribly illuminating, because at the end of the day, we're just going to look at the formula and sort of use it. I think it's worth deriving other concepts, but I don't know about this one. So here's what the formula is, and then we'll jump into actually using it shortly. Oh, and actually, I want to go back. Someone was asking about how do we get the terms here, or the 5 repetitions. So we got 5 repetitions from this part because if you think about the polynomial in more general fashion, that's degree 4, you would have, let's say, I need to use something else. How about P0 plus P1 of t plus P2t squared plus P3 t cubed plus P4 t to the 4th. So this t to the 4th in general is something a little bit more like this polynomial. This is a general 4th degree polynomial. So the number of repetitions here, you get 1 repetition per term. So we have a total of 5 terms. That gives us the 5 repetitions. Here we just have like a C1. So it's just 1 term. We get 1 repetition. And then if we add those repetitions together, we get 6. So then the polynomial we multiply by is a 6th degree, or not 6th degree, but 6th term, which is 5th degree. And if that's not clear, just let me know and I can give some more explanation. So yeah, you look at the number of repetitions for each, and then you combine the repetitions between this part, which is the non-homogeneous part, and the complementary solution. Combine those 2 repetitions, we get 6, and that's the polynomial that you multiply by here, where 6 is the number of terms. So 5 plus 1 is 6. So we get 6 terms, which will take us to a 5th degree. All right, so let's jump back here. And again, if it's not super clear, let me know and we'll jump back to it. So this particular formula here, it gives you a format for a particular solution. Now let's right away ask ourselves, what is this here? This is something called the Wronskian. So what is the Wronskian? So the Wronskian of 2 functions is the following. I'll just simply write it. The Wronskian of y1, y2 is equal to, we're going to look at determinant. So we may want to look at determinants in general and talk about matrices. I'm not sure what people remember and don't, but from the past, it hasn't been super immediately accessible. Probably been a while since some of you have seen this, but you take the 2 functions, put it in one row, and then you take the derivative of the 2 functions, put it in another row, and then we compute the determinant. And we'll go over more of this in a second. I want to check chat. I think someone asked something. Okay, so we'll come back to this Wronskian real quick. Someone was asking, what are these A0, A1, etc.? These are just undetermined coefficients in this case. So when you're multiplying by this, what you're doing is multiplying by a polynomial with undetermined coefficients. In the past, if you had, let's say, x double prime plus 9x equals 7 e to the 2t, you would pick the particular solution to be equal to, in this case, since there's no repetition between the complementary solution and the non-homogeneous part, you would have a times e to the 2t, where a is just unknown, but you will be able to solve for it once you feed this particular solution back through the differential equation. We say A1, A0, A2, etc., because there are just more of them, but they're essentially all these things like A that are undetermined coefficients. So you just have a bunch more of them. And we number them just because we don't want to use like A, B, C, D, E, F. It's sort of easier just to stick with A and number it. A sub 0, A sub 1, but they're all undetermined coefficients. Same with the b's. They're just like this. Okay, so the Wronskian is this thing. Now, just a quick check. Would you say in chat, and remember, only I'm going to see it, and I'm not judging you. I just want to know what it is. When I say determinant, offhand, do you feel you can compute a determinant for a matrix? Just for a matrix. Don't worry about functions at the moment, but just for a given matrix. So if I ask you to compute the determinant of this thing, can you compute the determinant of this matrix? I want to get a sense. Do people have no idea what this is? Is it really clear? So just in chat. Remember, only I'm going to see it. And I'm not judging you. I just need to know where you're at. Okay, it's looking like kind of a mix, which is usually what I expect. Some people are like, yeah, I can do that right now. There's a good chance you might have just had a class in it or used it, in another class if you didn't just like see it straight away. But for a lot of other people, you may not have used it for a while. So yeah, it's a minute. But luckily, it's not too difficult. Let's say we look at a matrix with numbers instead of functions to begin with. So I guess this will be a review of determinants. So if you've seen it, it gives you a little chance to just check your understanding. And then for those who haven't, it'll be either an introduction or a refresher. So first, well, let me change this name because it's not accurate. This would be determinants. If we have a 2x2 matrix, that's going to be 2 rows, 2 columns. If we have that, it might look something like this. If we then go ahead and compute the determinant of this, and let me maybe call this matrix A, the determinant of A, which is exactly the same thing as writing the same matrix, but with these what look like kind of absolute value bars instead of the either curved or I guess bracket style notation here. So if you do this, where you just have these straight bars, it can be a slight difference, but it looks like something more akin to the absolute value bars. Either way, it's the same thing, just different notation. What that's going to amount to in the 2x2 case is it's going to be A times D and then minus B times C. Now, this does have some meaning. It's not just, quote unquote, some random math formula. Namely, this determinant gives you an area spanned by 2 vectors. So if you have, so this you may or may not know, even if you know how to compute the determinant, if you have 2 vectors, one vector is like so, and it has components A and C. Oops. And then you have another vector like so, and it has components B and D. Like this, and these 2 are vectors. Then the determinant is looking at the signed area of the parallelogram between these 2. So if you look at this area, and we call that A is going to be equal to exactly this number here. So there's some geometric notions and intuition here that you can rely on. It's not just like, oh, there's some random combination of things. It is meaningful. And if you just try to do some geometry on this, it's kind of a fun little thing to do if you like to do that sort of thing, which I do sometimes, not all the time though. If you do the little bit of geometry, you can show that computing this area is exactly doing this here. Now, you can then scale it up if you have bigger determinants. Like if you have a 3x3, a 3x3 matrix, you're going to essentially end up doing some combination of smaller versions of this, where you have just a bunch of 2x2 matrices. You can alternatively, instead of just working with real numbers, you can use functions. Let's do some real numbers really quick. Say we have a matrix B, and it has values 1, 3, 7, -10. Based off of what we have here, and if you already know how to do this, this should be straightforward, and if not, it gives you a chance to practice. What do you think the determinant of B will be? So we have 1, 3, 7, -10, the determinant of B, and again, you can just say in chat here, only I'm going to see it, so you don't have to worry about a class knowing that you got it wrong. Determinant of B is what? As far as you understood it from before or understood it now? Okay, got about half the people. So the determinant will end up being 31. The reason being is why? We're going to first start by taking A times D, which is in this case 1 times -10. So we take 1 times, well, there's 1, times -10. Then we subtract from that the off diagonal entries multiplied together. So then we subtract 3 times 7. So this is like our A, this is like our D, this is like our B, this is like our C, where this is like A, B, C, D. And that, of course, gives us -10 minus 21, which is -31. Now, we can do the exact same thing with functions. Suppose you have two functions. Those functions are, let's say, f1 is, how about cosine of 3t? And then f2 is sine of 3t. If we set these up in a matrix, let's say we have a matrix A, and we set this up as f1, f2, which I'll write as the matrix cosine of 3t, sine of 3t. To compute a determinant, you need a square matrix. It could have like 20 rows, but it would need 20 columns. It could have 500 columns, but it would need 500 rows. So the rows and the columns, it must be the same dimension. If here we have two functions and we want to compute a determinant, well, that means we need another row. If we were to put just f1, f2 again, if you know anything about matrices, you know essentially that you have then a singular matrix. That is, you're going to get determinant 0 for sure anyways. And it's going to tell you nothing, like no matter what f1, f2 are, you always get 0 if you just repeat it. So in order to get a new row, we have to do something different. But we can get that new row from f1, f2. So what we'll say is that the next row is f1 prime and f2 prime. Computing that here, we have -3 sine 3t, and then we have what? 3 cosine 3t. Now let's suppose that we take the determinant of A, and you can probably guess, I'm going to ask you to take a guess at what it is. If we want to find the determinant of A, take a guess what you think it is, and I'll give you maybe a minute to think about it. But put it in chat if you think you can find what the determinant of this is. Okay, so I see a chunk of people have got it. Well, I don't see anyone simplify it, but you got the idea. You take and you multiply the diagonal first in the 2x2 case. Now, if we do that, we'll get 3 cosine squared of 3t. And then we'll subtract the product of the off diagonal, which is negative 3 times sine squared of 3t. That, of course, is 3 cosine squared 3t plus 3 sine squared 3t. You can factor out the 3. And that leaves you with cosine squared 3t plus sine squared 3t. And do you guys know how this simplifies? I can write something very simple. What can I write now? Yeah, good. 3. So this will just give you 1. And so we get 3 in the end. Yeah, nice. And that's really all there is to it. Now, this was a nice case because you have sine and cosine, and this determinant happened to work out. So you just get 3. But if it's some other expression, whatever it is, when we compute the Wronskian, it's just simply the final expression we get from doing all this. So I'm going to jump back to here. So what's going on with this formula here? Well, we compute everything based on finding the solutions to the complementary solution, or finding the terms of the complementary solution. Then you've got a Wronskian to compute. Okay, that's a determinant like we just did. And this says g of t, but really I mean f of t. But then you're just combining these expressions all in terms of t, and you're finding the antiderivatives. So it's just a matter of, can you find the antiderivatives of these expressions? And let's look at an example right away where I am going to pull this along so we can see what the formula should look like. So let's do this one. Let's go x double prime plus there's a particular one I wanted to do. I'm just bringing it up really quick. Okay, yeah. X double prime plus x is equal to tangent of t. All right. Now, tangent is not sine cosine, so we can't immediately come up with what the particular solution should be, as we've done before, because it's not an exponential, it's not a polynomial, it's not sine cosine. So we'll use variation of parameters here. You can use variation of parameters in those other cases, the exponential, sine cosine, and polynomial, but usually you want to save it for other cases, such as tangent here. Now you could try just guessing at a potential candidate, like maybe you just try, I don't know, a tangent of t, but you'll find out that doesn't work. You could try x of p is equal to, you might think, oh, how about a tangent t plus b secant of t? Because secant and tangent are often paired together like sine and cosine are. You'll find that that doesn't work, and so on and so forth. So you could try some things out, but go through, you'll find that they don't quite work. So in place, we can just use this formula. Now the y's will be x's and so on, but this will be our reference here. So let me put this kind of to the side here. Now I should go back and say, just to answer someone's question, that indeed the Wronskian is a determinant. And we're going to compute that in a bit here once we find our y1, y2. So we'll find y1, y2, and then we'll compute a determinant. Or in this case, our x1, x2. So let's go ahead and do that. So let's take and find the complementary solution. Without spending the time on it, I think you're all very capable of doing this. What we'll end up with is C1 cosine of t plus C2 sine of t. Oh, and someone had an interesting suggestion. Yeah, indeed, you could try rewriting tangent as sine over cosine, and then try making a guess at the particular solution there. That was actually something I tried in a previous semester, TAing this class just to see if it would work. And I wasn't able to get anywhere. There might be something fancy you could do, but just rewriting tangent I found didn't help me at least. But it's a interesting thing to try. Now, once we have the complementary solution here, we've got two parts. We've got x1 and then x2. Then we can consider our tangent of t to be the f of t, the non-homogeneous part. That gives us x1 is cosine of t. That gives x2 is sine of t. And then finally, f of t, as it were, is tangent of t. While we're at it, let's compute the Wronskian. So the Wronskian of x1 and x2 is going to be a square matrix. We'll start out with x1, x2, and then that's not quite square yet. So we need another row. In order to get it to be square, to get that other row, we'll take the derivative of each of these. Now we've got our 2 by 2. This absolute value bar, or set of bars here, tells us that we're taking the determinant. This will be the determinant of cosine t negative sine t, and then we have sine t and cosine t. If you compute that, I think you're going to get cosine squared plus sine squared, and that's going to be equal to 1. So this is just a slightly simpler version of the example we just looked at, where we computed the determinant. All right, so that's actually pretty straightforward as far as the Wronskian. Sometimes you'll end up with like an exponential or something else, but whatever it is, it's simply going to fit into the formula here. Now our x of p is going to be equal to, first we have x1, or negative x1, then the integral of x2 times f of t. And I'm really right now just rewriting the variation of parameters formula. That would be divided by the Wronskian, but we just saw that the Wronskian was 1, so there's nothing more to do there. Instead, we just have dt. Then we're going to have plus x2 times the antiderivative of x1 times f of t. And that's dt. The Wronskian is just 1, so we're just dividing by 1. This is the formula we want to use. Now let's actually substitute in the functions that we have. So we have negative cosine of t, antiderivative of sine t times tangent of t dt, plus x2, which is sine t times the antiderivative of cosine t tangent t dt. And now let's take this to another page and then we'll compute it. We've got two integrals to do. Here's one, here's another. This one happens to simplify cosine times tangent if you rewrite it as a sine over cosine, as someone suggested earlier, just in general. Then what you'll get is the expression being sine here. That's an easy enough antiderivative to do. And then in the other case, it's a little more complicated expression, but I think in the end is not too much more complicated. Is that true? Sine squared t dt over cosine t Actually, I'm drawing a blank on that one for a second. Yeah, at any rate, we're going to do this integral. May as well do that one. That's easy enough. And we have negative. Oh, I know how to do this. Cosine t. And let's see, how do I want to write this? I'm going to rewrite it like so. Let's see, cosine squared is 1 minus, or sine squared is 1 minus cosine squared. Yeah, there we go. For a second, I was worried that I wouldn't remember. And this is so far plus c. And in fact, we'll just end up leaving that off for now. And well, let me put it in because you may wonder why we could potentially leave this c off, and I'll call this C3, I guess. Okay, so there are some questions. Let me try to answer those. Someone asks, what if we have a messy, and yep, someone caught, it would be this. Is that true? Yes, it would be true. So thank you for the catch on the negative. Someone asks, what if we have a really messy w in the denominator, like e to something and multiplied by tangent of theta and that sort of stuff? Okay, that's a good question. Yeah, what you can do with this depends on what kind of integrals you end up with, and then just can you solve these offhand? If you had something like, let's say instead of this, and I'll talk about how to do this one in a second. There's a reason I wrote it like so. If you had instead maybe e to the t, just to make it not too crazy, cosine of 2t dt. Something like this is an integral we could do. This might be done using integration by parts, I think twice, or I can't remember, it might be integration by parts once and then plus a rewrite or trig substitution. No, not trig substitution. Just, yeah, I think integration by parts twice. I'm thinking of cosine squared. So something like this would be doable. If you end up with what someone suggested was maybe an e to the t tangent of 2t dt, something like this. I am not sure offhand how to go about solving that. I would try an integration by parts, see what I came up with, and then try to go from there. I have a feeling that you can find an antiderivative, but don't quote me on it. If you end up with something where you definitely cannot find an integral, like it's known that no mathematician can, it's just not possible, such as e to the t squared is kind of the classic example of a function that you cannot find an antiderivative formula for. It's just not possible. So if you were to end up with something like this, I mean, since you can't find the antiderivative, you would just leave that as part of x of p. And we saw a few examples earlier in the course where we would end up with integrals and we just left them. In fact, one of the problems on a homework was to compute the area of an integral that I claimed you could not do, you could not find the antiderivative of, or would be maybe too complicated to do so. So in that case, especially with something like this, you would just end up with an integral in your particular solution. But that's okay. Sometimes we just have to leave them. Now let's see. Some other people are saying in chat. Oh, yeah, someone asked a good question. What if your Wronskian is 0? Aha. Yeah, I like that question a lot because it actually brings up something important. So what if the Wronskian of x1, x2 is equal to 0? Well, from the the solution formula we had, that would immediately pose a problem. Let's jump back here. If you had this Wronskian 0, well, one, your formula would now not work at all. You cannot use this formula. And moreover, if we think about what that is, the Wronskian being 0, one can check linear independence actually using a Wronskian. So if you were to have the fact that the Wronskian of x1, x2 is equal to 0, that would actually imply that x1, x2 are linearly dependent. Now, what the problem with that is x1, x2 came from the complementary solution. And what's supposed to happen in the complementary solution is you have linearly independent terms. So in fact, as long as you found x1, x2 correctly, they should be linearly independent, which means that their Wronskian should not be 0. So this is a nice way to connect to linear independence. So saying that again, if the Wronskian of two functions, or 3, or however many, if the Wronskian is 0, they're linearly dependent. If the Wronskian is not 0, they're linearly independent. Now that's something you don't need to remember, but it does come up here. And it's kind of interesting. So you wouldn't have to worry about that so long as you found the right x1, x2, because they would be linearly independent. That's a good question. Actually, all questions are good, but I'm glad it connected to something else. Someone else also asks, what does the Wronskian say about the equation characteristically? Does it somehow classify it? Yeah, that's interesting. I actually don't know the answer to that. I mean, it's certainly true that looking at whether the Wronskian is 0 or not does tell you something about these functions. Even if you didn't already know they were linearly independent or not, checking the Wronskian would tell you. And either 0, yes, they are linearly dependent. Not 0, that means they're linearly independent. As far as like what value you get and what does that tell you about the two or the equation, I'm not sure offhand. I feel like you may be able to do some classifications saying that Wronskians of this type means you have a complementary solution of a certain type, or you have a differential equation of a certain type. Maybe you can classify your equations according to what Wronskian you get, but I'm not sure offhand. These are good stuff. Good questions. Now let's finish this just so we've done it, because it was confusing me for a second. So potentially you were not sure either how to do this integral. Now notice that I rewrote sine squared as 1 minus cosine squared. That's just because sine squared t plus cosine squared t is equal to 1. And of course, you can just subtract the cosine squared. Then you divide the cosine. You get secant of t minus cosine of t dt, which gives you two integrals to do. And if you do those integrals, what you'll come up with, you may or may not remember that the antiderivative of secant is ln of secant t plus tangent of t. And then you have minus sign. And if I'm being very careful, that's also a C4 over here. And now if we take all this, which I'll put on a new page, and simplify, I'll maybe run through the simplification just for the sake of time. What we're going to end up with is a positive cosine t sine t. We're going to have a minus sine t cosine t. then we're going to have a plus C4, or actually I guess minus C4 cosine t minus C3 sine t, and then finally minus cosine t times ln of secant t plus tangent of t. That simplifies down, and I'm going to claim that the actual particular solution you want is going to be negative cosine of t ln of secant t plus tangent of t. Now, the reason I say that, one, is because cosine times sine, that product cancels itself out here. And two, we don't actually need another cosine and another sine. The reason being is we already have that. In the complementary solution, we already have a C1 cosine of t plus C2 sine of t. If you then add in this part, it just gets sort of absorbed into this part anyways. So it's really just another version of the complementary solution. So we just take the part that isn't already the complementary solution. So the only meaningful part is this one here. And that's essentially it. I may have made some maybe algebra mistakes just trying to run through the work fast, but that's the large idea. So questions you guys have on that you want to ask quick? Yeah, so it may have been confusing what I did back here. Back here, I did actually do the multiplication. I took negative sine t times cosine t, and that's why I got this here. So this multiplication is this here, and then there's a C3 times sine, and that is this here. So I just did the distribution or multiplication, and then I kind of moved things around just so I could see how they cancel real quick. And the reason I ended up with only this thing is, well, these two cancel, so that we just, they cancel out anyways. And then with these, they're already in the complementary solution. So this cosine, if we were to just add it to the particular solution, once you add the two together, you're not going to get anything new. You're just going to have another cosine, which will be absorbed, and you'll get like C1 plus C4 times cosine, but just call that C5 or whatever. So it's essentially more than you need. And the same is true when we look at sine. We already have sine in the complementary solution. Adding it in the particular solution, it'll just be reabsorbed. I mean, you can put your particular solution as having an additional plus cosine plus sine, but you'll see that when you add them both together, when you take x is equal to xc plus xp, that the cosine here is added to this cosine, sine here is added to this sine, and you haven't really added anything new then. All right, I think that is our time. I apologize we didn't get to written homework 4, but I think we can look at that on Wednesday, depending if you rather look at that or do more review. But you guys have a good day. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.